All right, here is your last set of notes for Unit 2. So we are on Lesson 6, which starts on page 7 of your green notes packet. So this should be the last set of notes that you need. And this lesson is on bond polarity and molecular polarity. So they are definitely related. Bond polarity is just talking about the bond, and molecular polarity is talking about the entire molecule. So I'll show you the difference and a few examples of each of those. So section 8.4, just as a review for that first bullet point, remember covalent bonds share their electrons. So when we're talking about polarity, all polarity, whether it's polar or nonpolar, is referring to covalent bonds. So these will all be covalent bonds that we are drawing and looking at. So nonpolar covalent bonds are when the electrons in a bond are shared equally. So nonpolar means no overall charge. So if you have O2, which would look like this as a molecule, if you think about tug of war, oxygen would be pulling equally to one side, the other oxygen is pulling equally in the other side. Since both sides are equal, the rope is not going to go anywhere. So since there's no pull in either direction, then the molecule would be nonpolar. So nonpolar means that those electrons are shared equally, which means there's no pull in either direction. Polar means that there is a pull in one direction or the other. So polar means when electrons, or a polar covalent bond, is when the electrons in a bond are not shared equally. So when there's unequal pull from each atom. So if you have HCl, if you think again about tug of war, hydrogen is pulling one way with one, a certain amount of strength. Chlorine is pulling in the other direction with a different amount of strength. So because hydrogen and chlorine are different, their pulls are going to be different. And when you have different pull, then you have a polar molecule. So polar means that one side of the tug of war would win because the molecules are not pulling equally. So in a polar molecule, you have partial charges. So one side is going to be partially positive, the other is going to be partially negative. So the more electronegative atom will be partially negative. The less electronegative atom would be partially positive. Now, if you remember from Unit 1, we skipped the last page on periodic trends. Electronegativity was one of the trends that we were going to discuss. So we're going to kind of tie it in now a little bit. So the more electronegative will be more negative. The less electronegative atom will be more positive. So these are the symbols that you'll see for partially positive and partially negative. So for example, if we look at the chart of electronegativity, so each atom is assigned an electronegativity value. Electronegativity is how likely or the tendency of an atom to attract electrons. So over here on the far right of the periodic table, these are the elements that usually form negative ions. And so these will have a higher electronegative value or electronegativity value because they're more likely to gain electrons, whereas metals over here are more likely to lose electrons, so their electronegativity value is lower. So if you wanted to write down the definition for electronegativity, you could add that to your notes. But this is how we are coming up with these values. So this chart will represent how to figure out if the bonds are ionic, polar covalent, or nonpolar covalent. So when you're looking at this table, you find the electronegativity difference. So in math, when you find the difference, you are subtracting the values. So you just find the two elements that you're comparing. You take the higher number minus the lower number, and you find the difference. If the electronegativity difference is greater than 1.7, the bond would be ionic, which would generally mean a metal and a nonmetal. If the bond, or if the electronegativity value is between 1.7 and 1.4, that will represent a polar covalent bond. And if the electronegativity is less than 0.4, that would represent a nonpolar bond. So again, the smaller difference in electronegativity will mean that those electrons are shared more equally, and so there's no pull in either direction. And you will always have a copy of this table, whether it looks like this or is just in a chart, you will always have a copy of those values. All right, so now we get into the molecule overall. So a polar molecule is when one end of the molecule is slightly positive and the other is slightly negative. And this is due to shape. Dipole is another term that you will hear. Dipole means that a molecule will have a partially positive and a partially negative charge. So when you have a polar molecule, you have a dipole, or that molecule has a dipole, because one side is pulling more than the other, which results from the partially positive and partially negative charge. So the shape ultimately determines whether a molecule is polar or nonpolar, which we'll get to a few examples in a minute. All right, so here's two examples. One is polar and one is nonpolar. So when you're looking at carbon dioxide, so the drawing of CO2 is here. If you think about oxygen playing tug of war with those electrons, since one side has oxygen pulling and the other side has oxygen pulling equally, those poles are going to cancel each other out. So CO2 is going to be a non-polar molecule, because since both sides are oxygen, both sides of the molecule are pulling on those electrons equally. So that would be a non-polar molecule. H2O has these two electrons that are bonded to the hydrogen, but then on top it has these lone pair of electrons. So the lone pairs are different than the bonded pairs. So really you're looking for asymmetry or differences. So since those electrons on top are different than any bonded electrons, you have a difference in poles. So this molecule would have a dipole. The oxygen is going to be more negative. The hydrogen side will be more positive. So those poles do not cancel each other out, which means that that molecule as a whole is polar. So we'll look at a few more examples here. So if we have HH, if you think of hydrogen pulling tug of war, you have hydrogen on one side pulling, and you have hydrogen on the other side pulling. So since this hydrogen is the same as this, the pull is going to be equal. So the rope will not move if they're playing tug of war. There's no overall pull in either direction. So this molecule would be nonpolar. If we look at CO2, same thing, think about tug of war. This side of the molecule would be pulling the same as the other side of the molecule. Since these are both oxygen, they're pulling with the same electronegativity strength. So this side of the tug of war is going to equal out to the other side of the tug of war. So this would also be a nonpolar molecule. Water has these two lone pairs of electrons. So because these lone pairs of electrons are different than any bonded electrons, that difference is going to cause one side to pull on those electrons more than the other. So in water, this side is actually more negative, and the hydrogen side is more positive. So since there is a difference in how those electrons are pulled, this would be a polar molecule. All right, so I'm going to grab my last few examples. All right, so here are the last few examples that we will go through. SO3, this is the structure for SO3. So this shape, and this is where the shape really comes into play in your drawing. This shape is trigonal planar. So because sulfur does not have any extra electrons, these three oxygens are going to pull equally on the sulfur. So these three are going to be equally spaced, which means it'll be symmetrical. So when you have a symmetrical atom or symmetrical molecule where all three atoms are pulling equally, that pull is going to cancel out, and this would be a non-polar molecule. If you have NH3, now we have this lone pair of electrons on the central atom. So those lone pairs are going to be different than any bonded pair. That difference causes the molecule to not be symmetrical, which means that it would be polar because those electrons are not being shared equally in that atom or in that molecule. All right, the last one is CF4. So once you have it drawn, this shape would be tetrahedral. If you think about tug of war with this molecule, fluorine is pulling this way, fluorine is pulling this way, so those two dipoles would cancel out. Fluorine here is pulling down with a certain strength, but then this fluorine is pulling up at the same strength. So since these are all fluorine, all of these dipoles are going to cancel out, making this molecule nonpolar overall. Since these are all fluorine, they will all cancel each other out. However, if this fluorine was replaced with a different element, like bromine, because bromine has a different electronegativity than fluorine. So now this bromine is pulling differently than these three other atoms are. So with that one change, now that would make our molecule polar because this side no longer makes it symmetrical, that the molecule overall would be polar. Hopefully that helps.